Hey guys, how's it going? Welcome back to VESTA. I'm Manas Sharma, and in this tutorial I'll be showing you guys how to model an hBN, that is the hexagonal boron nitride monolayer, using VESTA. So we'll be learning how to model an hBN monolayer, as you can see right over here. And here is a 5x5 supercell of that. And by the end of this tutorial, you'll also be able to model something like this very quickly and very easily. Okay, so let's begin. Now the first step that you need to do is to obtain the CIF file or the structure information for the hexagonal boron nitride. And in order to do that, we'll head over to this Ripper Tools web app that I created for the TurboMol program package. And once you're here, you'll need to find the materials project to Ripper module in the sidebar menu. Just go ahead and click on that. And now once you're here, you need to enter the formula. So boron nitride has the formula BN, of course. So just type in BN and hit enter on your keyboard. Then it will do some processing, and you will get a lot of these results from the materials project database. Now the one that we are looking for is the stable form, so we'll need to check which of these is true, which of these is stable column value is true. And here I can see one, and as expected, this is the hexagonal crystal structure. So let's go ahead and download this structure for this MP604884. So here you will enter this structure ID MP604. Yeah, so here it is. And now if you scroll down, you will notice that here you can see the bulk unit cell of the hexagonal boron nitride system. And here you will notice that it's kind of like a van der Waals material, so there are no covalent bonds between the two layers of the boron nitride. So you just have one boron nitride molecule, or just atoms stacked over the boron nitride atoms of the other layer. And here we have an AB stacking. But okay, anyways, now what you're going to do is you're going to download the structure file. So let's say I click on the conventional cell. For this particular system, there is no difference between the conventional or the primitive cell. So let's go ahead and open my downloads folder and open this structure that I just downloaded. So here it is. Now, as you can see, here is some more, here is a view with more atoms, because VESTA loves to add these atoms beyond the boundaries and add the boundaries, which not a lot of software do. For example, the web app that I showed, that wasn't displaying the atoms at the boundaries, that was only displaying the atoms within the unit cell, or only the non-equivalent atoms. It wasn't displaying all the atoms at the corners because they are supposed to be equivalent. So in order to get a similar view in VESTA, what you can go ahead and do is you can go to edit, then go to bonds, and then select this particular bond and say do not search atoms beyond the boundary, and this way you will get rid of a lot of spurious atoms. But here still you are seeing some equivalent atoms. For example, all these four corner atoms are equivalent to each other, so you can also get rid of those by going to objects, then going to boundary, then selecting the X max to be 0.99, a value that is very little or like slightly smaller than 1. So 0.99 for all those, and then hit OK. And now you will see that now you're only seeing the unique non-equivalent atoms in the unit cell. So but still you have two layers. So in order to model a monolayer, we need to get rid of these one of these layers. So one way to do that would be to just select the upper layer atoms as so, and then hit delete. However, the other way that I'm also going to be showing you is to go ahead and hit on edit, then go to edit data, then go to I don't remember, maybe unit cell, yeah, not unit cell but structure parameters. Yeah, so here you can see that there are four non-equivalent boron nitride atoms, and two of those are at the base of the Z axis, and two of them are at the center of the unit cell. So let's go ahead and get rid of the 0.5 Z value atom, so this one and this one. So we'll just go ahead and select them and get rid of those and hit apply. And now if you come here, you will see that indeed now you have gotten rid of the other layer as well. And next, the only thing that remains is that we need to add a vacuum, because you're modeling a monolayer, so we don't want to be interacted. I mean, in a monolayer there's no repetition along the z-axis, so but when you model or run DFT simulations using software such as Quantum Express or WASP, then of course they have periodic boundary conditions built in. So that's why no matter what you provide, they will replicate it along all the A, B, and C lattice vectors. So in order to avoid these periodic images from interacting with each other, because those interactions are actually spurious, you won't observe them in experiments or real life. So you need to add a bit of a vacuum to avoid those. And the way to do that would be, just hold on a second and let me arrange the size of my window a bit. Okay, I cannot do that. Anyway, so in order to do that, you'll again go back to unit cell and simply just increase the C value to, let's say, 15 angstroms, which is usually sufficient, and hit apply. And here you see now your unit cell is much longer along the Z-axis, so there won't be any spurious interactions between the periodic images, because now the periodic image of this monolayer will appear right over here, so which would be sufficiently far apart. And now what you can do is you can click on OK. So this is how we have modeled the hexagonal boron nitride monolayer. If that is enough for you, you can also go ahead and just click on export data. So you go to file, then export data, and then you can say okay, hBN and unit cell. So this is just the unit cell of the smallest possible unit cell of the hexagonal boron nitride monolayer. So you can just call it that and export it as let's say safe. So you can do that. Now if I show you the zip file that we just generated, hold on a second. So let's open it using VS Code, which is the editor of my choice. So here you can see that okay, A and B lattice parameters are still the same as your bulk system, while the C lattice parameter is now 15 angstrom to representing the large vacuum, and you have 2 atoms in the unit cell. You can also export it as you can also export it in the VESTA format, that is the postcard format, by going to export data, selecting WASP, and then typing in again hBN monolayer unit cell and hitting save. And then you'll have to select Cartesian coordinates, because that is what I prefer. That is my personal preference. You can also select fractional or direct coordinates, and then you can just select okay, output current unit cell and hit OK. And now if I go ahead and open this postcard, then again I will see the same thing, that okay, I have the lattice parameters A and B corresponding to the same as the bulk one. Then the C lattice parameter is 15 angstroms, and then I have the coordinates of the 2 BN atoms. So that is mostly now we have reached almost the end of the tutorial. Now the only thing that is left to do is to construct a 5x5 supercell of the hBN monolayer, and that is fairly easy. You can finally just you already have the structure. You go to edit data, you go to unit cell, you go to transform, and here you can just enter along the so basically the diagonal entries correspond to the lattice vector A, B, and C. So here you can basically enter 5x5 if you want a 5x5 monolayer along A and B. Hit OK, select yes, then say search atoms in the new unit cell and add them as new sites. Hit on OK, then hit OK again, and that is it. So that is your 5x5 monolayer unit cell of the hexagonal boron nitride. And once again, you can go ahead and export it, let's say in the VESTA format. So you can now just say add 5x5 to it, and and then hit on save. Again, select Cartesian coordinates, output current unit cell, OK, and then you can open it with VS Code to check whether everything was done correctly or not. So here you can see that the lattice parameters along the A and B have now increased in their size because of the supercell, and also now you have like 50 atoms here, because the unit cell had 2 atoms, and a 5x5 monolayer will have 25 times 2 atoms, so that is 50 atoms. So that is what you have here. So so that is I think basically it for this tutorial. That is how I've showed you guys how to model a hexagonal boron nitride monolayer using VESTA. I hope you guys enjoyed this tutorial and found it useful. In case you did, then don't forget to hit the like button and subscribe to my channel for more videos like this. Thanks for watching and have a great day.